Hey, welcome to the Bioinformatics Chat. This is Roman. Before we start, I have a small announcement to make. I'm going to have to significantly reduce the amount of time I spend on producing this podcast. I actually considered declaring it finished, but maybe I won't go that far. Still, the episodes are going to be much less frequent and regular than before. And I realize they haven't been exactly frequent. But, if you stay subscribed, I might surprise you with an episode once in a while. As for today's episode, it was first published on the Compositional Podcast, which is another podcast I help produce. The background for the episode is that Twig.io, which is a company I work for, and also the company behind the Compositional Podcast, has a fellowship program. As part of this program, they give out stipends to people, not necessarily students, by the way, to work on cool open source projects for 3 months. And so this is an interview with one such fellow, Apostolos Chalkis, who worked on a Python package to analyze steady states of metabolic networks. I hope you find this interesting, and if you want to learn more, I'll link Apostolos' blog post, which goes into more detail and demonstrates how the package can be used. Apostolos, tell us a bit about your background. What were you doing before you started your fellowship?
I'm a PhD student at the University of Athens in the Computer Science department. I'm in my third year of PhD. And so before Twig Fellowship, I was working on my PhD topic, which is on computational geometry and statistics. And more precisely, I work on Markov chain Monte Carlo sampling with applications in bioinformatics and finance. But actually, most of the time of my PhD, I work on existing or new geometric random walks for sampling high-dimensional distributions. And I also write open source code. Actually, I implement those methods or the new algorithms we design and so on.
Yeah, that's very cool. And so, normally when we hear Markov chain Monte Carlo, we think about sort of Bayesian inference and the standard Bayesian methods, and maybe we don't immediately think about computational geometry or random walks. So maybe you could expand a little bit on how you approach this subject.
So my work is on more on high-dimensional distributions that are truncated on convex sets. For example, polytopes. You can think a polytope as a 2D polygon or a 3D polyhedron, and so a polytope is a polyhedron in higher dimensions. And for those distributions, the issue is that, and the problem is that the distribution is truncated, and so you have to work on special algorithms and methods in order to sample from it. And also there are specific applications in Bayesian statistics and specific models that require sampling from truncated distribution. So this is a specific thing on my PhD. And the random walks and in this case are called also geometric random walks, because you have geometric objects and specific structures on your problem that they have geometric interpretation. So there is a lot of geometry that you have to handle and work on.
Yeah, so just in case it wasn't clear for our listeners, when you say restricted distribution, you already described what a polytope is. It's a n-dimensional polyhedron, and so your task is to sample random points from this polytope, right? And the random walk is how you do that, right? Is how you pick points at random from the polytope. And maybe you could describe like a very simple scenario where we need just a uniform sampling. So we have a polytope and we want to pick a random point at uniformly distributed random point from this polytope. So what's the simplest way to do that?
We can take, for example, hit and run algorithm, which is a popular algorithm to sample from a polytope. And actually, hit and run, what it does is that being at a point in the interior of the polytope, it selects a random direction. And then this direction forms a line passing through that point. Okay, so through that Markov point, which is the current point of the random walk. And then this line hits the boundary of the polytope. So we have a point, a random line passing through that point that hits the boundary of the polytope. And then what you do is that you compute the intersection of the line with the polytope. So you have a segment now. Okay, so you have a random segment passing through your point. And then you select a random point, a uniformly distributed random point on that line. And this is your next point of your random walk. Okay, and then you move to that point and you continue the same procedure. You pick another random direction, you have another segment, and you pick another point.
And so you start from the point that you sample on the previous step, right? But you only pick the random direction at each step.
Yeah. In each step, you pick the random direction and you compute the intersection with the polytope, with the boundary polytope. And the billiard walk, which is a much more efficient random walk, it does the same thing, but when it hits the boundary, this line is reflected. So it performs several number of reflections, boundary reflections, and then it stops and takes the new point.
So you can come up with different algorithms, but some of them are more efficient than others. So how do you measure this efficiency of a random walk?
Yeah, the difficult part also here is that as you go in higher dimensions, and you, for example, you perform one step of your random walk. So you are at point X, you move at the point Y, and then at point Z, and so on. And you store all of these points. For example, you store 1,000 points. Then those points are not uniformly distributed on the polytope. Okay, if you do it for a 2D polygon, then it might be, but if you do it for 100-dimensional polytope, then no way. So the efficiency of a random walk is the number of steps that you have, or the number of Markov points that you have to burn, not to store. Okay, so such that at the end, the point that you store is uncorrelated with the starting point. So the efficiency is the number of steps that you have to perform in order to forget where you start from. So you start at the point X, and you have to perform a sufficiently large number of steps in order to forget X. So there are random walks that they forget the starting point very quickly, or there are other random walks that they forget it, very slowly. And this is the efficiency.
Is that how the algorithm actually works in practice? Does it make, let's say, 10 steps for each one point that it remembers? Or is it just a notion in order to explain the efficiency, but in practice you store all those points?
In practice you don't store all of these points. It depends on the random walk. It depends on the efficiency of the random walk. Because if you are in very high dimensions, the number of points that you have to store, if you store all of them, okay, the number of points that you have to store to obtain a uniform sample, for example, is too large to store it in a computer. So you have to burn points in order to be able to store them. Okay, and then you try experimentally to find a good walk length. We can refer to it as a walk length, the number of points that you burn, in order to have a sample that is sufficiently close to a uniformly distributed sample.
So maybe we could introduce the notion of the effective sample size. And from what you're saying, what I get is we want the actual sample size not to be much larger than the effective sample size, because if it was much larger, it would be just inefficient from the point of view of like storing all the data. So we want to bring the sample size closer to the effective sample size.
Exactly. As you increase your walk length, and for example, you fix the number of points that you store. Okay, so let's say that we sample 1,000 points, and then as you increase your walk length, and at the end you store 1,000 points. At the end you are going to have a sample that the effective sample size of it it's much larger. And just to be to clarify it, the effective sample size is the number of independently distributed point from the target distribution that your sample is equivalent to.
How do you define that equivalence?
If you want to use your sample to make an estimation, right, to estimate a quantity, then the effective sample size is the accuracy that so when you use your correlated sample, okay, you are going to get an accuracy. And the effective sample size of your sample is the answer to the question, what is the number of independently distributed points that are going to succeed the same accuracy with your sample.
Wouldn't the accuracy depend on what exact statistic you're trying to estimate? So if you're estimating the mean versus the variance versus some other versus the median, wouldn't the accuracy be different between all these cases?
Actually, always you try to estimate a value of a function, right? So this function is also a random variable because you sample from a distribution. So your points you sample are also random variables. So the quantity you estimate is also a random variable, and it has a variance, okay, itself. So every function that we estimate has a variance, and this is the notion of accuracy when you make an estimation with a sample.
But again, it would depend on the function you pick, right?
Yeah, it depends on the function you pick, and when this variance is large, then you don't have a good accuracy. You have to increase the number of points that you have to sample. Okay, so as this number increases, as you sample more number of points, then the variance of any function that you estimate gets smaller. But there are functions that you have to sample, for example, 1,000 or 2,000 points, and this is okay. But there are functions that you have to sample much more points to have the same variance.
And so what I get from this is there's no like standard effective sample size, but there is an effective sample size per function. So you need to specify what function you want to estimate, its expectation.
Exactly.
And then with respect to that, you get an effective sample size. So we went pretty deep into the computational geometry and mathematics. Let's now get to the biology, because you did a lot of interesting stuff with the biological applications. And first, I'm curious how you ended up in the realm of biology. Why did it interest you?
Actually, at some point of my PhD, I read a paper about metabolic networks, and that there is a specific approach to analyze those networks with sampling. Sampling actually uniformly from the interior of a polytope. So you can represent the network as a polytope and then sample and so on. So there were many papers on that, and from my research I knew that I could improve it. So I could design a new method that it was better than the existing ones. But my problem is that I didn't know almost anything about biology and metabolic networks. So at that point, I remember that I had a friend in Crete, in the University of Crete, at Heraklion, at the city of Heraklion, that does his PhD on bioinformatics, and he has a biology. Background. He graduated from the biology department at the University of Athens, and I just wrote at him an email, asked him, what do you know about this specific problem, or what do you know about metabolic networks and so on. And the interesting thing here is that he was also very interested on that problem, but his problem is that he didn't know almost anything about computational geometry and sampling. So we united our forces, and we work on that problem. He helped me with the biology, and I helped him with computational geometry and sampling. And we came up with a new method for analyzing networks with sampling. Yeah.
That is awesome. Yeah. And let's now introduce this notion of a metabolic network. What is it?
Yeah. Actually, every organism or a cell, or in an organ or in any cell, there are many or thousands or dozens of thousands chemical reactions that are taking place. But on the other side, the products of its reaction affect any other reaction. Because its reaction, what it does is that it takes a number of reactants inputs and has a specific number of outputs. Okay, the product. So in an organism, these inputs and outputs affect each other. So the inputs and the outputs of its reactions affect the inputs and the outputs of any other reaction, because maybe reaction A products a metabolite that is used to another reaction as an input, and so on. So you have a network that each reaction affects the other one, and this affects another one, and so on. And the thing now is that when you leave this model to run for a sufficiently large time interval, what this network does is that tends to balance. Okay, if you assume that it's not affected by its environment. Okay, the number of metabolites that are for each metabolite, the quantity that is produced is also consumed by other reactions. Okay, so and this holds for every metabolite. So then the quantity of metabolites that all the reactions needs is equal to the quantity of metabolites that all the reactions produce. And this is called the steady state of the metabolic network. When the rate of production is equal to the rate of consumption, then we say that the network is at a steady state. Okay, and this is the states that we're interested in. We actually we want to study the network under the assumption that it is on a steady state.
Yeah, and it's good to mention that it's just an assumption. It's not like we're pretty confident that it's not what actually happens in an organism, because there's always dynamics, there's always change to which our organism responds. But it just turns out that this assumption often is a useful one. It's very hard to analyze this large scale network if you also add all the dynamics of it, like how it evolves with time, but as simplifying assumptions, let's consider the state where everything balances out. And so you wrote this package that does some analyses on the metabolic networks and more specifically on the steady states, like it discovers the steady states of metabolic networks. So what are the different approaches to the discovery of steady states?
Yeah, actually there is a very popular method that is called FBA to analyze metabolic networks. And what FBA does is that...
And let's clarify, it stands for flux balance analysis?
Yeah, flux balance analysis. And the first more important assumption that FBA does is that the biomass of the network takes its possibly maximum value. So the biomass is the total quantity or weight of the organism in a given area or volume. So we assume that the network is in that optimized state. It has this optimized behavior. Okay, and then what FBA does is that it computes a steady state that corresponds to that optimal behavior.
Right. So if we didn't do that, if we didn't impose an objective function, we would just have too many steady states, right? There's not a single steady state. There's typically a lot of steady states. So we need to add some additional constraints or objective functions to specify which one we want.
Yeah, and this is I think this is a half of the whole truth, because it is true that there is an infinite number of steady states, and also there is an infinite number of optimal steady states. Because actually, what is a steady state? The steady state declares the rate that its reaction is taking, the activity of its reaction. So when you have so what FBA does to study this set of steady states, because you can find an infinite number of steady states, is to impose, yes, as you said, additional constraints to compute an optimal steady state. But again, the thing is that there is not a single optimal steady state, but actually FBA imposes an additional constraint just to be able to obtain an optimal steady state. But there are also an infinite number that is not taken into account by FBA. And this is the main drawback of FBA, that first it cannot handle the initial space where you don't impose an additional constraint, where you
what is that additional constraint?
That the value of the biomass takes its possibly maximum value.
Oh, okay. So that's the constraint you refer to.
Yeah. So if you don't impose it to the network, then FBA does not work. So FBA cannot take into account the steady states that have any other value that corresponds to any other value of the biomass of the network. So this is the first drawback. So you cannot study your network in an unbiased, let's say, state, in an unbiased behavior with respect to the biomass. And the second is that, okay, let's impose that we have an optimal behavior of our network. So the biomass takes its maximum value. Then again, there are an infinite number of optimal steady states, but FBA can compute just a single one. Okay, and this is the second drawback, that there is too much information that FBA does not take into account. Okay, and this is where we come and where flux sampling comes, and what it says that, okay, let's impose this additional constraint. Okay, what we do now is that we describe mathematically the set of this optimal steady state, which is a polytope.
Yeah, so that's exactly where this discussion connects to our previous discussion, because the listener may be wondering, like, why did we have this weird discussion about polytopes and random walks? But it all comes together right now because, as it turns out, the steady states of a metabolic network, they actually form a polytope, right?
Yeah. Exactly, and this is where computational geometry meets metabolic networks. And moreover, this is where Markov chain Monte Carlo sampling meets biology, because the next step is to sample from that polytope, to sample uniformly distributed points, which is equivalent to generate uniformly distributed optimal steady states of the network. So of course you assume that every optimal steady state has the same probability to be picked by the network, okay, and then you sample optimal steady states, and then instead of a single optimal steady state, okay, in the case of FBA, you have you generate as many as you like, and then you can do a statistical analysis on that set. And what you get is that you have much more information than FBA can provide. Okay, of course you don't have any guarantee that you are going to that sampling leads always to a better result or a more sophisticated conclusion about your network and so on, but this is, of course, it depends on the problem, on the specific structure of your problem, of the question that you study. But for sure you have much more information that you can handle and work with to try to lead to a much more to enrich actually your conclusion.
Yeah. And one other question we should probably cover here is, why do we need sampling at all? So the steady states, they form a polytope, which is a properly defined geometrical object. And if we need to do some analysis, we could do this analysis on the polytope directly. We can have its analytical specification, and if we want to estimate some function, so the expectation of some function over the polytope, I'm guessing there exist analytical methods to do that. So why would we resort to sampling here?
Actually, we need sampling because we in higher dimension we cannot use the explicit representation of a polytope to estimate the quantity that we are interested in. For example, as the dimension grows, you cannot compute integrals over a polytope, or you cannot estimate probabilities distributions that corresponds to random variables that you are interested in. And so in lower dimensions, of course, you can compute those things exactly, but in higher dimensions it is not it's not possible to do it. So you need sampling, you need from certain distributions in order to estimate those quantities.
And what would be these quantities, for example?
In metabolic networks, the main problem is to have an estimation about the fluxes of the reactions, and then try to correlate those fluxes with the biomass or with other biological quantities and so on. But everything starts from the fluxes, which represents the activity of its reaction. And the important thing about sampling is that you can model your uncertainty about fluxes with using as much information as you can. And more specifically, you can use sampling to estimate a probability density for each flux, and then have the whole story about your flux. Instead, for example, having a single value or something that you cannot be sure how possible is to be picked by the network. So yes, having a single value, you don't know how possible this value is to be picked. So using the sample, you can have a statistical model for your fluxes.
So you were working on this Python package called Dingo that implements these algorithms. Can you talk a little bit about what Dingo can do at this point?
Yeah, Dingo performs three methods for analyzing metabolic networks. So it can be used only for metabolic networks, and it can compute it can perform FBA, or another method that is also very popular, which is called flux variability analysis, and this is FVA. And the third one is flux sampling. And Dingo uses the method that we have developed with my friend from Heraklion at Crete, and use this Markov chain Monte Carlo method to generate steady states. And then it can also perform some statistical computations and so on to help you analyze those steady states.
Cool. And actually, by the time this podcast is released, there will be a blog post on Twig's blog where you show how to apply your package to some interesting data. So please go and check out the blog post. We'll put the link in the description of the podcast. So in terms of the future plans, do you have any particular research directions that you'd like to explore after this?
Yeah, actually I will stay on this kind of Bayesian models. First of all, the next step on that specific problem of metabolic networks is that there are also larger metabolic networks that Dingo can sample from. There are, here I have to say that Dingo is the most efficient package for sampling, right? For sampling metabolic networks. I mean, it can sample from the latest human metabolic network. But there are some metabolic networks that have never been analyzed before. So Dingo was the first package to analyze Recon 3D, which is the latest human metabolic network. But there are also some even more high-dimensional networks that we are not able to sample from them. So the next step is to improve more the algorithm. So we need the new algorithmic tools and some specific things on the random walk that we have to improve, and also improve our implementation, our code. And then the next step is to sample from those networks. And also there are a few things that I want to complete for my PhD. It's again sampling for other Bayesian models.
And by the way, one thing that we should mention that we didn't somehow mention before is that your package not only does uniform sampling, but you can also incorporate the objective function. So it's a sort of like a middle ground between the completely unbiased uniform sampling, and FBA, which optimizes a specific objective function, and you can incorporate that objective function, but more like probabilistically. Can you talk a little bit about that?
Yeah, actually, as we said before, you can consider the steady states that that you haven't imposed any value of the biomass on them. So you can so you have the set of all possible steady states, and here let's say that you have the set of optimal steady states. And while FBA forgets about the first set and goes directly to the second one and computes an optimal steady state, our approach is that you can incorporate this function, this biomass function, and then define actually distribution, or the thing is here that you make an assumption that you say that the higher the biomass value is, the higher the probability that its steady state is going to be picked. But it does not necessarily have to be an optimal steady state, but it can be close to be an optimal steady state. So we incorporate this function, and we define a proper distribution that we sample from it, and then we have this we unify those two approaches. We have the set of all possible steady states, but also we have high probability to select steady states that has higher biomass value, but not necessarily an optimal biomass value. And then so we add a bias here. We have instead of imposing a specific value, we impose a biased behavior for the steady state. We say that we have high probability to pick high biomass value, and then we can also parameterize this bias. So we can impose a very strong bias for this probability. So and also we can lower this bias, which actually is uniform sampling. So
it acts more or less like a Bayesian prior, right? You can have either a strong prior or a weak prior or no prior at all, at which point you get a uniform sampling.
Yeah, exactly. You can start from an agnostic prior, and then you can finish to optimal steady states. And you have a distribution that unifies those things. You unify agnostic, prior with a certain biomass value. Okay. You can unify those things. Agnostic prior with FBA. Yeah.
All right. Well, Apostolos, it was great working with you, and good luck in your future research.